All right, we're going to get started with our notes for Unit 2, Day 2, or we'll be calling this Day 2.2. We're talking about rotations and dilations, and you'll see that on the other page. All right, so we're going to kind of use both of these pages. You picked both of them up in class. This is the page you want to start on, where we talk about rotations, okay? If you are not on the correct page, it's not going to make any sense with what you're supposed to be writing down, because it's not going to fit in the right blanks. We're going to talk about rotations first. A rotation is simply a turn around a fixed point. We call that fixed point the center of rotation. Makes sense, right? The figure rotates around a specific, or at a specific angle and direction. Okay, the directions are either counterclockwise or clockwise, okay? Counterclockwise is opposite the way the hands move on a clock. So to the left and around, starting at the top, going backwards around the clock would be counterclockwise. If it goes the same direction as the hands on the clock, then it would be clockwise. But we are going to focus our rotations around a center of rotation at the origin. That means we're going to rotate everything around the origin, and we're going to rotate it in our coordinate plane around that. There are plenty of other ways I could set up a center of rotation, but that is what we're going to stick with for right now. So we're going to look at some rules using a counterclockwise rotation around the origin. And these are the only degrees we're going to use. We're going to use 90 degrees, 180 degrees, and then 270 degrees. I'm going to give you these as portions of a full circle. Okay, assuming that a full circle equals 360 degrees, a 90-degree rotation is a 1/4 turn. A 180-degree rotation is a 1/2 turn, and 270-degree rotation is a 3/4 turn. Okay, I want you to remember that we always put our transformations in terms of our pre-image being the original notation letters. That says pre-image. It's written pretty tiny, but pre-image. And that transforms into what we call the image with our prime notation, A prime, B prime, C prime. So on each of these, we are starting with this as our pre-image in the top right corner. We would call that quadrant 1 of our graph. Okay, quadrant 1. And we are rotating according to this number of degrees in a counterclockwise direction. Quarter turn, half turn, 3/4 turn. And there are rules we're going to follow for that. We are going to start out with our mapping rules like we always do, x comma y. Now, I'm going to show you what these rules are without really telling you why we get them that way. And I'll explain it as we go. So if I'm just going to do a 1/4 turn, or a 90-degree rotation around the origin, that takes the x value and turns it into a new x value called -y. And it takes the y value is now what the x was. So what this means is, to find out your new coordinates, you're going to switch the x and y coordinates, but you're going to make the y its opposite number, leaving the x the same positive negative value. To change a half turn, we can think of that as 2 90-degree rotations. So if I followed this same rule and switched them again, making it another negative value for this one, when x switches back and makes it negative, it looks like that. And when y moves over here, it's still -y. So a 180-degree rotation is just like 2 of these. We switch the negative positive values, but we keep x and y the same for a full 180-degree rotation. X turns into -x, y turns into -y. And to do a 3/4 turn, x turns into positive y, and y turns into negative x, which is kind of backwards from what we see here. We still switch the x's and y's, but we make the y value negative for a 1/4 turn. I'm sorry, the new x value. We make this first coordinate the negative, or opposite, in a 1/4 turn. In a 3/4 turn, we make the second value, or this new y value, negative. So it's really important that we just use these rules the way we're supposed to. So again, in this video, we're not going to do every single example. We're going to do an example or two with each page of the notes, and we'll do more in class. But make sure you're following along as best you can and learning from what we do here. Okay, we are going to start with example 1 here. We're going to graph and label each figure and its image. That means pre-image and image under this given rotation. It's going to give you a degree and a direction. Okay, this is counterclockwise. We are sticking with counterclockwise most of the time. So what I want to do first for number 1 is plot the original points A, B, and C. And we should get a graph that looks kind of like this. Okay, there's A, B, and C. A is at 2.7, B is at 6.5, C is at 4.1. If you need time to pause this video to copy it down, make sure you do that. And we are going to rotate this 90 degrees counterclockwise. So it's a 1/4 turn this direction. So we're going to follow our 90-degree counterclockwise rotation. We're going to use this rule. So we're actually going to write it out. We're going to start with A, 2.7, turning it into A prime by taking your x and y values and switching places and making this first one its opposite sign. So 7 is going to move to the front and become -7, and the 2 for the x value moves to the y value as a 2 now. So we're going to plot that point, -7, 2. So I go over here to -7 and up 2. There's A prime. B is going to follow the same rule. We're going to start with 6.5. They're going to switch places, and 5 becomes negative when it switches places. Same thing for C. We start off with 4.1, and we turn it into -1, 4. Now, if you're not sure about if that's right or not, if I were to take this and actually take the original and turn this paper 1/4 turn, that's where my space ended up in the second quadrant. If I think of this as my y-axis now and this is my x, these ordered pairs end up being these ordered pairs I just got. Okay? That's another way you can check your work. So we're going to try and do a 180-degree rotation. We're actually going to do number 4. We're going to follow our rule for a 180-degree rotation. Notice it does not say counterclockwise or clockwise. And that's because when I do a 180-degree rotation, if I start here and I go 180 degrees this direction, I end up in quadrant 3. But if I go the other direction, I still end up in quadrant 3. So it doesn't matter for 180 degrees whether it's clockwise or counterclockwise. Okay, so we're going to plot our original points and get triangle XYZ that looks like this. Okay, and we're going to rotate this 180 degrees. So it's going to end up over in this space. But we're going to follow our rule for a 180-degree rotation, and that's to take every x coordinate and y coordinate and turn it into just the opposite x coordinate and the opposite y coordinate. So that's what I'm going to do. 3, -2 turns into the opposite of 3 and the opposite of -2. So that's my x value. My new x prime is -3, 2. So I go to -3 and up 2. And there is my x prime coordinate. My y prime coordinate is going to start with 6, 1 and make it -6, -1. 6, negative 1. And then z prime goes from 5, negative 7, and turns into negative 5, positive 7. Okay, so really it's just memorizing these three rules that help you to be able to do rotations. So we will take a look at some more rotations in class next time, and then we will move on in our notes to our lesson on dilations. Now, what I want you to understand about dilations is that they are a little bit different. Okay, when we talk about dilations, notice that these triangles, this preimage and image, are not the same size. And these dilations are a transformation that change the size of our figure but keep the shape the same. Now, we are going to take a look at this and work through these, but you need to understand that transformations we've talked about so far, reflections, translations, rotations, are all considered congruence transformations because your preimage is congruent to your image. They're the same shape, same size. But with dilations, we are changing the shape. I'm sorry, we're changing the size, not the shape. So let's take a look at what dilations mean. Okay, a dilation is where we take either the enlargement or reduction of a figure. And we use something called the scale factor. And that indicates how much the figure will either enlarge or reduce. And so there's some rules to follow here. We call the scale factor, our variable for scale factor is letter K. K is just the variable we use for scale factor because S and F have different meanings in algebra and geometry, so we're just using K for scale factor. Now, when that K, it's going to be given to you like this. When we have our scale factor K, it's going to give it to you as a number. When K is greater than the number 1, this is an enlargement. Okay? Because we're multiplying by a factor bigger than 1. We're increasing size. But when our scale factor is less than 1, and we will never have a negative scale factor, what this really means is that K is between 1 and 0, so it's a fractional scale factor, then that dilation is a reduction. Okay? So we're going to practice this a little bit. We're going to start with our original figures, and then we're going to apply our scale factor and get our images after the dilation. So we want to start by plotting the original for triangle RST on example 1. R is at negative 5, 1, 2, 4, 5, up 1. And notice your scales on your graph are different because we're actually changing size now. S is at negative 3, 4. So that's R. S is at negative 3, 4. And T is at 2, negative 1. So we're going to plot that figure. K equals 2, that is a bigger number than 1, so this is an enlargement. And what we're going to do is simply take each of these ordered pairs and multiply their coordinates both by that factor of 2. Scale factor means we multiply. So R prime will be negative 5 times 2 and 1 times 2. That gives us negative 10, 2. S prime will be 2 times negative 3 and 2 times 4, or negative 6, 8. And T prime will be 2 times 2 and 2 times negative 1, or 4, negative 2. Okay, so when I plot these points, negative 10, 2, there's R prime, negative 6, 8 is S prime, and 4, 2 for T prime sorry, for negative 2, t prime, is there. And you will also notice that with an enlargement or reduction, in this case an enlargement with scale factor 2, each point is twice as far from the origin as its pre-image point. Okay, we're going to do one more example here. Take a look at number 3. We're actually going to use a scale factor this time. It's a rhombus we're using, 4 sides. They're all going to be the same length, but that isn't important right now. We're going to use our scale factor of k equals 1/2. That is less than 1, so this is a reduction. We are going to end up with half the size that we started with. Okay, so we plot the original points, and it should look like this. Okay? Pause the video and make sure you copy these down correctly. But that's our original figure, and we're going to reduce it by a factor of 1/2. And so here's what that means. For j prime, we're going to do half of negative 10, because 1/2 times negative 10 is the same as doing negative 10 divided by 2. We're going to do half of 2. Well, that gives us negative 5, 1. And for k prime, be half of negative 2 and half of 8, so on and so forth. So we're taking half of each of these. So k prime is negative 1, 4. Half of each of these coordinates for L prime gives us 3, 1. Half of each of these coordinates gives me negative 1, negative 2. So j prime is at negative 5, 1. K prime is at negative 1, 4. L prime is at 3, 1, and M prime is at negative 1, negative 2. You'll notice that the corresponding sides of your image and pre-image are parallel in this case. Okay, most of the time that should work out to be the same. All right, we're going to do some more work with dilations and rotations, and we're going to talk about something called symmetry when you come back into class, but this gives you a start for our lesson.